Dear learners, welcome to the video lecture on basic logic gates. Logic gates are the building blocks of all digital electronic circuit. Your multiplexer, flip-flops, the microprocessors, computers are all built with these logic gates. In this lecture, you are going to learn about 6 logic gates: OR gate, AND gate, NAND gate, NOT gate, NOR gate, and exclusive OR gate, their construction, their truth tables, and verifying them. So let us start learning about the logic gates.
A logic gate is a digital circuit which processes the digital signals. It processes the signals basing on some logical relationship. That is the reason why we call it as a logic gate. A logic gate is the building block of all digital electronic circuits. The logic gates have input and output as binary numbers, that is zeros and ones. For each logic gate there is a unique symbol or logic diagram. So it is used to represent and identify the logic gate in any electronic circuit. The advantages of logic gates are they are smaller, cheaper, faster, and they consume very less power, and they can easily cascade it. That means they can be joined to form the larger circuit. There are three basic gates: AND gate, OR gate, NOT gate. These three basic gates are combined to form another three gates: NAND gate, NOR gate, exclusive OR gate. These gates are called combinational gates. There are other type of logic gates called the sequential gates. This is because the output of these gates depends upon the sequence in which the inputs are applied. Examples of sequential gates are registers, counters, and flip-flops. All the gates are constructed using diodes, transistor, MOSFETs, and their combinations. OR gate is the basic logic gate. It is an electronic circuit which has two or more inputs but only one output. It is called OR because it gives high output if one of its inputs is high. The plus symbol is used to show the OR operation. This is the logical representation or logical symbol of the OR gate. This is a two input OR gate. A and B are two inputs and Y will be the output. This electrical circuit shows the working of OR gate. Here A and B are two switches and this is a bulb. This is the bulb is the representation of the output. When the switches are open, then logic is taken as 0. When the switches are closed, then the logic is taken as 1. Similarly for the bulb, if the bulb glows, then the logic is taken as 1. And when the bulb is off, then the logic is taken as 0. When two switches are open, that is A is 0, B is 0, you can see here the bulb doesn't glow. That means the logic is 0. If A is closed and B is open, that is if A is closed, if you make it 1 and B is open, then the current flows in this direction and the bulb glows, then the logic is taken as 1. If A is open, you make A as 0 and B is closed, so you make B as 1. Then the current flows in this direction to the bulb and the bulb will glow, then the logic is taken as 1. If both are closed, A is closed and B is also closed, then the current flows in both direction, the bulb glows, that is the logic is taken as 1. You can observe here the pattern that if any one of the input is high, the bulb is glowing. So which is the working of the OR gate, which we call it as OR operation. The circuit shows a 2-input OR gate constructed using diodes. There are two diodes D1 and D2. This is the P terminal of the diode. This is the N terminal of the diode. The diodes will conduct if they are forward biased, and if they are reverse biased, the diodes will not conduct. These two are the inputs for the diodes. Now let us check the output and the input by varying the inputs. So I am making the input A as 0 and B as 0. When A is 0 and B is 0, both the diodes are reversed bias. When these two are reverse bias, they will not conduct, and hence the output voltage will be 0. So A0, B0, the output voltage is 0. Now I am changing the input condition. I am making A as 0 and B as 1. When A is 0, B is 1, then the diode D1 is reverse bias. So this will not conduct. But diode D2 is forward bias. This will conduct. Now the current will flow here. So we will get the output as 1. So when A is 0, B is 1, output is 1. If I make A as 1 and B as 0, so in this condition, the diode D1 will be forward bias and D2 is reverse bias. So D1 will conduct, D2 will not conduct, and the current flows through the diode D1, and again in this condition also we will be getting the output. So when A is 0, when A is 1, B is 0, the output is 1. And if I make both the inputs as 1, A is 1, B is 1, in this condition both the diodes will be forward bias and we will get the output. So the output will be high, that is 1. That is when A is 1, B is 1, the output is high. Hence we can verify the truth table of OR gate. The AND is a basic logic gate having 2 or more inputs and only one output. It is called AND gate because it gives a high output only if all its inputs are high. The AND operation is given by dot symbol. For a 2-input AND gate, the Boolean expression is given by y is equal to a dot b. This is the logical representation of AND gate. So in any circuit, this symbol is used to identify the AND gate. This electrical circuit shows the working of AND gate. There are two switches A and B. When the switches are closed, then it is taken as logic 0. When the switch is on, then the logic is taken as 1. Similarly, when the bulb is off, then the logic is taken as 0, and when the bulb is on, the logic is taken as 1. If you see in this diagram that the light glows only when both switches are closed. That is, when A is 1, B is 1, then only the light is glowing here. The light doesn't glow if any one of the switches is open. That is, if any one of the input is 0, then the light doesn't glow, which verifies the working of AND gate. The figure shows the electrical circuit of a 2-input AND gate constructed using diodes. Now let us verify the truth table of AND gate using this electrical circuit. Here A and B are 2 inputs and D1, D2 are the two diodes. This is the N terminal of the diode, this is the P terminal of the diode. The diode will conduct if they are forward bias and will not conduct if it is reverse bias. Now let us check the input condition. If I make A as 0 and B as 0, then the diode D1 and D2 both are forward bias. So hence these two diodes conducts. Now due to the conduction of these diodes, the current will be flowing in this direction to the ground. There will be no output here. So that's why we will get the output as 0. This when A is 0, B is 0, the output will be 0. Now I am changing the input condition. I am making A as 0 and B as 1. Now diode D1 is forward bias, it will conduct, and diode D2 is reverse bias, it will not conduct. Because diode D1 is conducting, the entire current flows through this diode to the ground and there will be no output here. So when A is 0, B is 1, the output is 0. Now I am changing the input condition again and making A as 1 and B as 0. Now diode D1 is reverse bias and D2 is forward bias. Because D2 is forward bias, it conducts. So the current will flow through D2 to the ground. There will be no output here, so Y will be 0. So when A is 0, B is 0, output will be 0. Now if I make A as 1 and B is also 1. In this condition, both diodes are reverse bias and they will not conduct. The entire voltage drops here, so we will be getting the output as 1. So when A is 1, B is 1, the output will be equal to 1. This verifies the truth table of AND gate. NOT gate is the basic logic gate having only one input and one output. It is called inverter gate because it gives a output that is always opposite to the input. That is, if the input is high, the output will be low, and if the input is low, the output will be high. A bar is used to show the NOT operation. The figure shows the logic symbol of the NOT gate. A is the input, then A bar is the output. The Boolean expression for the NOT gate is given by Y is equal to A bar. This is the small electrical representation of the NOT gate. You can see here, if the switch is open, that is, when the switch is open, we take the logic as 0. When the switch is closed, the logic as 1. When the bulb is glowing, the logic is 1. When the bulb is off, the logic is 0. When the switch is open, the bulb is glowing. When the switch is closed, the bulb is not glowing. That is, this circuit works as a inverter, that is a NOT gate. The figure shows the electrical circuit of NOT gate. It is constructed using a NPN transistor. Here the NPN transistor is in common emitter configuration. Now let us verify the truth table of NOT gate using the electrical circuit. Here A is the input. If input is high, that is V in is 1, then this is a NPN transistor in common emitter configuration. This is NPN. When V in is high, then the transistor is in saturation position. So the output will be 0 here. That is, when A is 1, the output is 0. Now I am changing the input. If I make A as 0, this is a NPN transistor. Now this is the base current here. When A is 0, then the transistor will be in the cutoff position. When the cutoff position, the output is equal to VCC, that is the output is high. So when A is 0, output is high. It verifies the truth table of NOT gate. NAND gate is the combinational logic gate. It has two or more inputs and only one output. NAND gate is formed by combining AND gate and a NOT gate. The output of the NAND gate is the complement of the AND gate. If A and B are the inputs of the NAND gate, then the output of the NAND gate will be A dot B bar. This is the logical representation of NAND gate. You can see here, this is the AND gate and the small bubble is the for NOT operation. So AND plus NOT gives the NAND. So you can be shown in this diagram also. This is the AND gate. When the AND gate is combined with NOT, it forms NAND. The Boolean expression for the NAND gate is Y is equal to A dot B bar. The circuit diagram shows a two input NAND gate constructed using diodes and transistor. Now let us verify the truth table of the NAND gate using this electrical circuit. Here A and B are two inputs, D1, D2 are two diodes, and this is a transistor, that is a NPN transistor in common emitter configuration. The diodes will be conducting if they are forward bias and will not conduct if they are reversed bias. Now let us apply the input voltages. So if I make A is 0 and B is 0, then the diode D1 and D2 will be forward bias. They will conduct. So the entire current will flow through the diodes. There will be no base voltage for Q1. Then the transistor is in the cutoff position. The output voltage will be equal to VCC, that is the output voltage will be equal to high. So when A is 0, B is 0, output voltage is high, that is equal to 1. Now I am changing the input condition. I am making A as 0 and B as 1. The diode D1 is forward bias, it will conduct, and the D2 is reverse bias, it will not conduct. So the current will flow through the D1 and there will be no current for no voltage for the transistor at the base. Hence the transistor is in the cutoff position. In the cutoff position, the output voltage is equal to VCC. VCC means the output is high. So when A is 0, B is 1, Y is equal to 1. Now I am going for the third condition. When A is made as 1 and B is 0, the diode D1 is reversed bias and D2 is forward bias. So D2 conducts. So the current will flow through D2 and there will be no base voltage for the Q1, and the transistor Q1 will be in the cutoff position. So in the cutoff position again VCC is equal to Y, that is the output voltage will be high. So when A is 1, B is 0, then the output Y is equal to 1. Now I am making A as 0 and A as 1, B as 1. In this condition, both the diodes D1 and D2 are reverse bias. These diodes will not conduct and there will be base voltage given to the transistor. Now the transistor is in the saturation position. In the saturation position, Y is equal to 0. That is when A is 1, B is 1, the output voltage will be equal to 0. This verifies the truth table of NAND gate. NOR gate is the combinational logic gate having two or more inputs and only one output. NOR gate is formed by combining OR gate and NOT gate. The output of the NOR gate is the complement of the OR gate. If A and B are the two inputs of the NOR gate, then the output of the NOR gate is given by the Boolean expression y is equal to A plus B. This figure shows the logical representation of the NOR gate. These are the two inputs, then this is the output. Here you can see here, this is the OR gate and this bubble is for the NOT gate representation. When these two are combined, this is called OR plus NOT, gives rise to NOR gate. The figure shows the electrical circuit of NOR gate constructed using diodes and transistors. So let us verify the truth table of NOR gate using this circuit. Here there are two inputs A and B. This is a NPN transistor which is connected in the common emitter configuration. These are the two inputs. Now I am making the input A as 0 and B as 0. When A is 0, B is 0, there will be no base voltage for the transistor. So the transistor will be in the cutoff position. In the cutoff position, the output is equal to VCC. So the voltage will be, output voltage will be high. So when A is 0, B is 0, output is high. Now I am making A as 0 and B as 1. When B as 1, this is given to the base of the transistor. Now the transistor is in the saturation position. In the saturation position, the transistor conducts. So the output voltage will be equal to 0. So when A is 0, B is 1, the output voltage will be 0. Now I am changing the input condition again. I am making A as 1 and B as 0. So when A is made 1, so this is connected to the base of the transistor. Now the transistor is again in the saturation position. The transistor conducts and the output will be equal to 0. So when A is 1, B is 0, the output voltage will be 0. Now I am making both the inputs as 1. A is 1, B is 1. In this condition again, there will be the base voltage given to the transistor. That transistor conducts because it is in the saturation position. The output voltage will be equal to 0. So when A is 1, B is 1, the output voltage is 0. So this verifies the truth table of two input NOR gate. Exclusive OR gate is the combinational logic gate which is formed by combining the basic logic gates. It has two or more input terminals and only one output. It is called exclusive OR because the output of this gate goes high when its two input terminals are at different logic levels with respect to each other. The logical representation of exclusive OR gate is shown in the figure here. This is a two input XOR gate. The Boolean expression for the exclusive OR is y is equal to a dot b bar plus a bar dot b. This is a electrical representation of the exclusive OR gate. If you see here, this LED glows when the two switches are at different levels. That is, when it is this switch is at this position and when this switch is at this position, that is two different levels, the LED glows. When these two switches are at the same levels, the LED doesn't glow. So this is a typical type of exclusive OR gate operation. This exclusive OR gate can also be seen in our homes. If you are having a light in the stairs and the light is having two switches, one is in the first floor and another switch is in the ground floor. When the two switches are on or when the two switches are off, then the light doesn't glow. In order to make the light glow, one of the switches must be on and one switch must be off. So this is the working of the exclusive OR gate. The equivalent circuit of XOR gate is shown in the figure. We can verify the truth table of exclusive OR gate using this circuit. This modulo symbol shows the exclusive OR operation. Here A and B are two inputs. Now let us make the input as 0. This input as 0. When A is 0, B is 0. This is 0. And this B goes to the NOT gate, and this NOT gate inverts it, it becomes 1. So 0 into 1, the output will be 0 here, and this is 0 to the NOT gate, this inverts it to be 1, and the second input to this AND gate is 0. So 1 into 0, the output will be 0, and when these two inputs are 0, the OR gate output will be 0. So 0, 0, the output is 0. Now I am changing the inputs. A is made 0, B is made 1. And this is 1, this A is 0 here, B is 1, B is given to NOT gate, this NOT gate inverts it, it becomes 0. So 0 into 0 to the AND gate, this output is 0 here, and this 1 is given to the AND gate, and 0 is given to this NOT gate, it inverts it, becomes 1. So 1, 1, the output will be 1. So 1, this is 1 to the OR gate, this 0 to the OR gate. So 0, 1 logic for the OR is 1. So when it is 0, this is 1, this is equal to 1. Now I am going for the third condition of the truth table. I am making A as logic 1, B as logic 0. When A is 1, the AND gate, this is 1, B is 0. For the NOT gate, the output will be inverted, that is, this will be 1. So for the AND gate 1, 1 logic, the output will be 1. And for the second AND gate, this is the input A. For the NOT gate, it inverts it, it becomes 0. If B is 0, then this is given to AND gate here, this will also become 0. 0, 0, then the output will be 0 here, which is given to the OR gate. 1, 0 logic for the OR gate is 1. So 1, 0 is 1. Now I am going for the fourth condition of the truth table. I am making logic A as 1, B as 1. If A is 1, this is 1. So this is also 1 here. It inverts it, it becomes 0. So for the AND gate 1, 0, the logic will be 0. For this NOT gate, if the logic is 1, then it will be inverted, it becomes 0. This 1 is given to the AND gate, this is going to be 1. So 1, 0 logic for the AND gate, it is going to be 0. So 0, 0 given as inputs to the OR gate, the output will be 0. So when 1, 1s are the inputs, then the output is 0. Thus the truth table of exclusive OR gate is verified. In this video lecture, we have learnt the construction of basic logic gates and 3 combinational logic gates. We have also learned the working, and we have verified the truth tables of all the 6 logic gates.
Thank you very much for seeing this video lecture. Thank you one and all.